All right. Now, welcome to MathSoc 2111 and 2011 seminar. Presenting today is myself, Otto Ois, Oscar Wellard, and Han Wang. Let's get into it. Okay. So, first up, we have curves and surfaces, followed by point set topology. I'm going to be covering these, and then I'm going to hand over to Han for these two, and the rest of the course content we'll be covering tomorrow in our seminar then, at the same time as today. Okay, so let's get moving. By the way, feel free to post any questions, queries, quibbles in our comment section below. We'll try and get to them as fast as we can, and it should be fantastic. Let's get on with it. So first up, curves and surfaces. In this topic, we're just going to be talking about how do we define a curve and what are some questions relating to that? How do we do that? Most of curves and surfaces is like a presetting for our later topics in the course as we're dealing with multiple variables and curves, surfaces kind of jazz. All right, so first up, what is a curve? A curve is defined by a parameterization from a simple domain, which is an interval on the real numbers, to Rn, which is some vector space. We have a definition for a closed curve, which goes from one point to another for two different periods of times, and we also have a multiple point definition. Okay, I'll touch on those just in a little bit, but first up, let's look at the limits and calculus for curves. So, for this little section, we're going to be looking at, okay, what does it mean for a curve to approach a point at a limit? Well, what we imply by this is that given that limits exist, component-wise, we have the breakdown of every component for a limit. Okay, so if we say that CT goes to CA as t goes to A, that is also implying that given that these are in vector spaces, we have the ith component of t goes to the ith component of A of that curve, okay? No longer vectors as they're just real numbers, okay? As t goes to A. Simple as that, if every component of a curve goes to a point, then the curve itself goes to that point. That's how the limits are interpreted in this sake. And we can also apply the same manner of logic to the derivatives. Okay? So the derivative of a curve is given by the component-wise derivative of the component curves from real to real. Okay? So note that these are not vectors anymore because they are not bold. Okay? We're dealing with single dimensions there. Okay? Moving on. We have some definitions for surfaces in R3, which is our 3D space. We got up, down, left, right, and forwards, backwards as our three manners of direction. And so there are three ways we can describe these surfaces mathematically. First up, we have a graph surface. So here we're taking a grid, essentially, and assigning numbers to all the points on that grid, which would denote how far forward or far back they are, determining a manner of 3D space. Additionally, we can describe a curve implicitly through an equation that equates to some manner of constant, where we can chuck the constant into the function and have the exact same manner of expression. What this tells us is that, okay, given some manner of function, let's say x plus y plus z equals 0, we can have this describe a curve. In fact, this would, form a plane that slopes down into the xz plane or something as you observe it. Things like that. But this is one way to describe it. Okay. Note that before we used a function of f and y, so we can actually convert this graphical interpretation into an implicit definition just by chucking our z to the right-hand side and then determining f of x, y minus z is our implicit function big F. However, we cannot necessarily go the opposite direction, because z might be like a square or something like that, which doesn't directly go into a nice little function. It might require multiple functions. Anyways, moving on, we have parameterization. Okay, a surface will take in two parameters because we're considering a surface which is the construction of lines, yeah? And that manner of thinking gives us some manner of surface, as you can consider the intersections of these points, right? So I think that's clear enough for right now, and we'll get moving on. So diving straight into a question, we have a certain surface. This surface is given by the implicit definition of x squared plus 3y squared minus z squared equals 1. We want to sketch the intersection of this surface with the xz and xy planes. We want to just do this quite neatly, so labeling axes, intercepts, asymptotes, and all of that stuff. Now, something important to note with this section is that we're talking about the intersection of this surface with planes. We can call this the level curves of this surface as a manner of, I guess, determining functions that describe our surface, give us more information. So, first up, with the xz plane, this is denoted by the plane given when y is equal to 0, and it kind of draws out it's like the intersection of them. So just here on the left, I'll draw out what I mean by the xz plane. We got directions x, y, and z going up. And so when y is 0, we have the xz plane, which is given by this manner of sheet, okay? I made a little mess, but I hope we get the point. Okay, and so by letting y equal to 0, we have x squared minus z squared is equal to 1. This describes a manner of curve, okay? We call that a hyperbola. Next up, we have the intersection of S with the xy plane. So if I make a similar little sketch over here, the xy plane is going to occur when z equals 0. So we have this lower sheet. And so, mathematically, that's represented by x squared plus 3y squared equals 1. And so, given some stretching of our y component, we arrive at a manner of ellipsoid, okay? An ellipse, where our y value is shrunk down from our x value, since it has a higher weighting. Okay, and so that is that question done, and we're going to just re-clarify some of our terminology. So a multiple point is a point on the parameterization of a curve that is passed in at least two distinct values of the time parameter. Mind you, these curves that we're talking about is some manner of function denoted by c for some parameter. We can call it time because sometimes we talk about the velocity of the curve and things like that. And so it's just easy to define it in that sense. So what this implies is if we have a curve that looks something like this with endpoints A and B, we have this point right here, which I'll just highlight in red pen, is a multiple point because it is passed in two distinct points in time of this curve. And then we have closed paths, whereby we have whatever jazz the curve goes through, but it ends at the exact same point. So it becomes closed, right? Quite intuitive, and we'll get moving on. Straight into point set topology. All right, so let's begin with the definition of what a ball is. Our definition of a ball is given by some manner of radius that we denote as epsilon, it has to be greater than 0, about some point. And so the ball is defined as the set of all points within whatever space that we're dealing with, such that the typically Euclidean distance from that point is less than our distance, okay? Note that this is less than and not less than equal to, okay? An important distinction. Something else that we can consider is what a punctured ball is, and that's going to be given for where the interior, we're only dealing with the contents of the ball, but not the center, right? So if the Euclidean distance is no longer equal to 0, as a passing statement, we have that A is not inside of this ball. So you can consider this in R2 as a circle. Mind you, this is a dotted open circle with an open center, right? And that would be a punctured ball. Okay, that's a bit of our definitions in, and now we're going to talk about a lot more of our set terminology, right? The big thing about set terminology is that we have these things called interior, exterior, boundary, and all other manners of points. So, what is an interior point? An interior point is a point such that there exists some manner of ball of some size, some non-zero size, for which all elements of that ball are inside the set. Now, some ways that we can think about this is, okay, if I have a set, okay, this little peanut thing, no matter what point I take inside here, let's say I take this point, okay, there exists some ball for which it is a subset of the entire set. If I take something almost on the boundary, there is some tiny, tiny, tiny ball that exists. The reason that we call this, that we can like talk about this as a open set, as like an extra definition of the set of points, is because there will always exist some manner of ball around here that satisfies that condition. We can get infinitely close, but as long as we're not on some manner of boundary, there always will be some ball that exists. But if we're on the boundary, there's always some ball that exists where the exterior also touches the outside, okay? So the outside of the surface is including, the ball always includes something outside of our set, right? And that's what we call a boundary point, right? So we covered interior points. We're going to give that a green tick. We have open sets, which are sets where every point is an interior point. Fantastic. Next, we have closed sets, which are the complements of open sets, right? So what do I mean by complement in this sense? Well, let's define a universal set. So let's say everything exists inside this box within some manner of R2 described here. If I have the set of this circle, the complement, actually I'll just call it A for the sake of the circle, the complement is everything on the outside, okay? So that's going to be the dotted boundary around that circle and everything else, right? So if I just get highlighter, too easy. It doesn't go inside the circle. All right, so we'll give that a tick. It's important to make this distinction about closed sets because then we're allowed to define, okay, is the set of the real numbers an open or closed set? And we'll find that, okay, its complement is the set of no numbers. And by some null distinction law, we know that the set of no elements is both open and closed. And so since open and closed work as complements, we know that the set of real numbers is also both open and closed. Okay. We covered boundary points because we are making the distinction that within the ball, within any size ball, right? we have, there exists 2 points in that ball where one is inside the set and one is outside the set. So we're making the distinction that within any ball on the boundary, so I'll just draw an extra circle here, any point on the boundary, there's some part that's inside, some part that's outside. And that's going to be for all size balls that exist. Fantastic. Okay, just a little bit of an extra distinction. We have this implication that a set is closed if and only if it contains all of its boundary points, okay? So that is also so to say that no boundary point can also be an interior point, which is rather intuitive. All right. Next up, let's talk about a few of our set theorems, okay? We know that the finite union or intersection of open sets is always going to be open, and the same rule applies for closed sets, right? We can consider this as very dependent on the word finite, because you can consider, okay, well, if I take the closed set from 0 to 1, and then attach that with the 1 to 2, 2 to 3, all these closed sets, and I go to infinity, both infinities in fact, I have the set of real numbers, which is open as well as closed, but it can invalidate these manners of laws, okay? So it's important to make that distinction about finite. All right, so diving into another example from the 2019 paper, we want to use the definition of, sets and openness to show that this set given by -3 to 1, which is a subset of the real numbers, is not open. So what do? We go ahead and we want to disprove this statement, okay? Because an open set says that all points are interior points, such that there's some ball that everything inside it fits inside the set. So to prove that it is not open, we need to disprove it. So we prove that there exists some of it that's not inside, okay? And that's going to be for all size balls. All right. So let's consider this. We have a number line. It is closed at -3 and open at 1. If I pick a number that's going to be super close, in fact, at -3, then any size ball I touch is going to go an epsilon amount over to the left as well, okay? Because balls defined on just the number plane are given by an open distinction about some manner of point, okay? Just as another application of our metric. Okay, and by that, quite clearly, we have it proven. Fantastic. We'll dive into what a limit of a sequence is and what limit points really are. That'll be our next component. So, first up, our definition. For a sequence of points, denoted by xi from I to infinity, within the space of Rn, we have that x is the limit of the sequence if and only if for all for all epsilon greater than 0, there exists some manner of natural number whereby your value at xk is going to be inside of this ball. So what does this imply? This implies that I can choose some epsilon for which there must exist a value n where if I have my limit right here, okay, at this point, I can say, okay, within any size ball, everything further inside of this series of points is going to exist inside that ball, okay? And I can choose epsilon again for an even smaller ball, and then there must be some value which gets even closer and closer and closer, implying that as epsilon goes to 0, we reach our limit, okay, which is our point x. Okay, Some extra clarification, this is called the limit point, okay? It's just determining that for some manner of sequence, we have it as the limit, which defines it as a limit point as its definition. So really, if I have some big set of numbers, I can determine that, okay, everything inside here, because there is space, can be defined as a limit point. Even these boundaries, because you can have a set of points which get closer and closer and closer and closer to the boundary, okay? Things like that. Okay. To show that something is not a limit point, we want to disprove this statement. So that's determining that there exists some size ball for which there's nothing further, okay? There's nothing further in the sequence that lies inside it. So that's saying that if we want to prove that this is not a limit point, then it's saying that there's no manner of sequence of numbers that remain inside this ball, okay? We can see this almost as like if we have our set here and then just a random included point offset, okay? There's no way we can have our points go towards that, because if I pick an epsilon ball that size, there's no way everything further in that sequence goes there, because I need to have like some manner of space, okay? All right, fair enough. And let's move on to interior and boundary points, okay? So interior sets, boundary sets. Our interior is the set of all interior points. So for some manner of space, our interior is just the inside, okay? Just the inside, because they are all interior points. There exists some manner of ball size for each of them. Everyone can have a different ball size, it doesn't really matter, such that everything inside that ball is inside the set. Similarly, we can consider boundary points, okay, which are going to be just the boundaries. Too easy. Everything is a boundary point. So the boundary of a set, the boundary set, is the set of all boundary points. We denote this with a little fancier, I think it's delta omega, okay? So moving forwards, we talk about the closure. The closure is some manner of set where if we have, let's take this set for example, okay? It has a boundary, but it's also got this little bit on the right-hand side which is open, okay? So it's you can almost call it the union of an open and a closed set, which is not entirely both. So our closure of this is determining that, okay, well, I know that these are boundary points on the outside. The closure will make them so, okay? And so it has an element of completeness, so we can determine that the closure of omega is such a shape where everything is included, okay? Both our boundary and our interior. All right. Now we have a certain lemma, okay? Just the implication between limit points, interior points, boundary points, things like that, okay? So first up, we have that if x is an interior point, aka it is inside, and there exists some manner of ball of some size that contains, you know, a subset of omega, which is a subset of omega, my bad, it must be a limit point. And how can we prove this? Well, if I have some point and there's an epsilon ball like that, I can say that really close. If I start my limit point sequence here, it can get closer and closer because there's space available, okay? So that is a tick, fantastic. Next up, if something is a limit point, what does it imply? It implies that it is either a boundary point or an interior point, right? Because it can go both ways. If I have a boundary point, then it can be a limit point. But not always, because it is possible to have some manner of, it's a tricky proof, okay? But we know that our implication goes this way. And be careful of the or, because implications, okay? If I have a limit point, I can limit towards a boundary, I can limit towards something inside the set. Simple as that. So that is a tick. Fantastic. So next up, we have, given that x is inside the closure, remember we're using a fancy symbol now. Given x is inside the closure, there exists some sequence in our set using like interior points, which has a limit of x, right? Because the closure is the union of the interior and the boundary. So we have that if we are inside this manner of shape, we're going to be a limit point. So it's kind of the backwards of our previous thinking. Fantastic. Okay, now, one more definition, okay? Maybe a few more. Okay, so first up, we want to determine what it means for a function to converge to a point, okay? Because convergence, it's a little funky. If I have a function that just dots all around the place, I can't really be sure of anything. So how can I become sure of stuff? Well, what I say is that there's some epsilon, okay? For every epsilon, there exists some delta such that given x is within some distance to some point inside my domain, right? My function of all those points here exists within another ball around the result, okay? So what's that implying? It's saying that, okay, let's take this circle and push it to this circle using f, okay? F is a manner of function. If you push a set through a function, it becomes a kind of mapping, okay? That's a way of thinking it. If I say, okay, A over here goes to B over there, okay, entertain me. If I say epsilon is going to be this big, so I have a ball there, then for there to be convergence, okay, for there to be convergence as x approaches A, so whatever point I'm using here gets closer to A, or is near A, it must exist within some manner of ball size to get there, okay? Because that is implying that as I get closer to my point A, I am approaching some point F, okay? So it does it in a very neat, this implies that, rather than, okay, this happens and that happens. The neatness surrounding it is saying that I can get infinitely close to my point B as my function result, and it implies that what I put into the function right here is within some distance of A, okay? And if it is within some distance of A, there's like, I'm getting closer, okay? So if I go really close to B, and I have a big area around A for which it can be, then that's saying that everything in this area is within that distance, including what's close to it, what's close to A, okay? So by a manner of backwards definition, it's saying that as x goes to A, the function goes to B, okay? Which is exactly what we want to describe. Fantastic. Any questions so far? Okay, I hope I'm entertaining you. So some more useful, not more useful, just some more useful limit theorems. We have limits imply the component-wise limit, as we described before for things like our parameterization of curves. And we also have this manner of limit definition can also be used for the limit points through a function, right? So in this example, we're using x right here. Actually, no, sorry. We're using A as our limit point x, okay? Our limit point x, and then as we take the as we take the function of the series of points which converge, that limits at x, our result is the function of that limit, okay? So limits work in a very nice way because of convergence, okay? With some setting up, with that being that, of course. Okay, now we have our second part of those theorems, which are going to be our standard arithmetic of functions and limits, given that, you know, you're not dividing by 0. Yeah, fair enough, fair enough. Well, we have, okay, things work in a very linear fashion here. That's all it really is, not much more to explain. Okay, now our favorite, it's time for pinching theorem. Pinching theorem is a theorem that describes, typically, when using just one variable, as this function goes here, and that function goes there, and they both kiss in the middle, we have that another function, which, sorry, that's not a function anymore, that's a relation. A function that can dabble however it likes, but is enclosed by these two, must also hit that exact same point, okay? We can describe a similar kind of motion within other sequences, okay? Sequences of functions, right? Function mappings. So what I'm really trying to say here is that if we say within some ball of inputs, okay? Within some ball of inputs, if everything here is sandwiched between one value and another value, then we can say that if those two values at any point within this space here, I'll just highlight it, if any of those points within that space there have it so that these two functions satisfying this inequality converge to a point, then your intermediary function must also hit that point, okay? So it's kind of bringing this to an n-dimensional space where we deal with f of x and g of x, g of x, f of x, and h of x in some manner of ordered fashion, sandwich f of x, okay? Nice. This will lead us into an example. And so, let's consider what this limit really tells us, okay? The limit as your points goes to 0, 0 of x plus y on the magnitude of x plus the magnitude of y. So, quite trivially, we know that this limit doesn't exist because the question is telling us prove that it doesn't, but also for the fact that intuitively, sequences of numbers exist such that the limits are different, okay? And what this means is if I talk about this space within a circle, okay? If this is like x, y, I'm treating this circle of spaces, okay? And the elevation will tell me, okay, what is that limit going to be? I'm just mapping this function essentially. Well, if I approach it from a perspective of, let's say y equals 0, x equals t, okay? Sorry, x equals 1 on k, k being greater than 0, right? So that tells me that, okay, the function becomes 1 on k over 1 on k, which is just 1 for k greater than 0. And so that tells me that, okay, going from this side, I have an elevation of 1, okay? Fair enough. As I go close to that point, which would give me a limit of 1. I can do another thing where, okay, what if I tack on a negative there? Well, we know that this point still approaches, this sequence still approaches 0, 0 as we go along, but our magnitude of our value takes place. So we add a negative there, and so we get -1 is our new limit from the opposite side. Okay, we're calling this x-axis, y-axis, all of that jazz. And so we describe two manners of interpretations of this function as they go to this point, which yields two different limit results. Well, if a limit is equal to two things and it's a function, it doesn't quite work because, well, functions are only valid for a single point, yeah? 1 to 1, pretty much, right? So for every x, there is some y. Not that there's two y's. Over here, we've demonstrated there are at least two y's. So the limit doesn't exist, okay? So over here, we show the exact same working as described above. You can use different values, it doesn't really matter, but the fact is that we're using a sequence of numbers to determine this fact, okay? Fantastic. So this brings us to example 3, 2016, a little far back, but still relevant, okay? We're going to be dealing with a sequence of, a function which we know the boundaries of, okay, and has a limit. Well, we can say that the limit of the inside of this as you go to 0, 0 maintains the limit because we're technically not still including that point 0, 0, okay? You can say as xy go to 0, 0, it remains less than or equal to 1, but anything else. We want to prove this limit, okay? Over here, we can clearly see that this is the construction of our given function and just tacking on another x. So we can apply our first and foremost arithmetic of functions and limits, okay? So that tells me that the limit of this is going to be equal to the product of the limit of this one and the limit of this one, okay? So taking absolute values, we know that we essentially sandwich this between 0 and negative itself and positive itself by taking absolute values. So by taking absolute values, we can go ahead and say, okay, first off, we know that this thing is going to be less than or equal to 1. So we have that the total thing is less than or equal to this limit as the absolute value of x goes towards 0, 0. And therefore, well, tell me what happens when x goes to 0 and what is x? Simple enough, okay? Fantastic. Next up, we got continuity, okay? We love continuity because continuousness is nice to assume, but we can't always do that. So what does it mean for continuity in Rn? Well, a function from some domain to Rm has it such that all limits are going to equal to that point, okay? Fair enough. It is continuous if this is for all points within that set omega, and just fantastic, okay? It acts as an extension of limits. And so, if we want to really get down to the nitty-gritty, we interpret this as per our limit definition. We say that for every epsilon, there exists some delta such that some delta ball around your point A, where x is points inside of your set, of course, because we're only dealing with a very strict domain, being omega, it implies that your functional values also exist within some size ball, okay? It's the exact same as our limit of our continuity of functions of limiting values, okay? Things like that. We jump onto some pre-image theory. So pre-image, it's just the inverse of functions, okay? We're talking going from omega to Rm, from Rm to omega, okay? Things like that. And so, if we take some subset of Rm, we know a few things about the pre-image, okay? The pre-image is defined by, okay, all y whereby the function brings us to that set, okay? And so, we have a very important theorem here. We have that a function is continuous if and only if it is synonymous to the fact that the universal, sorry, no, not universal, that this subset of Rm, if it is open in your set, okay, it implies that the pre-image is also open, okay? So that's saying that if I take some open set here and I do the pre-image of it, I get another open set. This is very important because continuity implies that I can take limits. Limits means I need space to take limits. So there must exist some ball around whatever points we're examining, okay, for those limits to take place, which is it's a really important factor to take into account of. So if I have some manner of ball over here, there's a ball around it, we know that that implies that there is some ball over here, yada yada, we have that inside this ball I can make a limit, which implies continuity. That's why we need to be like a little bit touchy around sets with closed boundaries, because we cannot be certain that there's continuity at that boundary. Yeah, we kind of like step into the void, the abyss, once we try and take a limit outside of our domain. Okay, one extra thing, we have that given an interior point of the image, right? And the fact that this point exists within some size ball, we have that the same point in the domain is an interior point of the pre-image of the ball, right? So it's a little bit finicky, but it's using the fact that, okay, well, as I said before, if I'm going from one ball here to another ball here, I say that, okay, within some ball here, there exists some size ball in here that satisfies closeness, okay? If that ball is bigger than that ball, well, that still implies that everything within this size ball is within the right magnitude from it, okay? Things like that. Okay. Straight into the next example, okay? Let's chug through this. So, given that a set is open and your function is continuous, what is known about the preimage of it? It's kind of what we just discussed. So, let's think about it. We have an open set as our image, and the function is continuous. What does it mean for it to be continuous? It means that you must have space for limits, which means that your preimage must be also open, right? So, through some very delicate work over here, we can compute certain limits which form very solid, rigorous proving statements which determine that we have a delta ball that exists entirely within our pre-image. And so, it is also open. Fantastic. All right. So, second last bit of theory. We have compact sets and bounded sets, right? So, a bounded set implies, mind you, I'll just quickly explain what this D means, but a bounded set is implying that here's our origin. Let's consider our theory. So we got our 6 lines, well, 3 lines, 6 directions. If I have a set, it is bounded if I can draw some manner of giant ball that encloses that entire set, okay? Just that it's bounded within it. It doesn't go to infinity everywhere, okay? Anywhere. Fantastic. So, what does this D mean? Well, it's our form of metrics, okay? D by itself implies a Euclidean distance, which is going to be, you know, your standard square root of x squared plus y squared plus yada yada squared, okay? If you use D infinity, well, that means that you're going to technically take the infinitieth root of x to infinity plus y to the infinity plus yada yada to infinity, which, you know, by some power assumptions, you can say, okay, that's just going to be the max of your components, x, y, yada yada, okay? And there's also going to be things like D0, which are just going to be, you know, the sum of your components. Things like that, You also have funky ones which are like, delta, which compute like 1 plus 1 on something else. It's a funky one because it isn't equivalent to the other ones. We can talk about equivalent metrics another time, but essentially the main gist of it is understanding, okay, a metric follows a number of rules which determine distance essentially, okay? Certain distances might be more important than others, but over here, and generally, we'll be considering the Euclidean distance, which is just, Pythagorean distance. Okay, so back to bounded compactness. Bounded, it exists within some manner of ball, okay? None of the set tends to infinity. So if I say, okay, the set of real numbers, it's not bounded because real numbers go to infinity. Closed argument. Fantastic. Next up, compact sets, okay? A set is compact if it is closed and bounded. So what does that mean? It means my boundary of the set is all solid lines. Simple enough. And they're all solid lines that I can see. It doesn't trail off to infinity. Fantastic. It exists within some size ball. Now note that this size ball, we denote it as being centered at the origin. It doesn't really need to be at the origin as long as it's at some finite point. Okay, we can't just place it at infinity and say, oh, hey, there's a ball there, it works. Trust me. No, sorry, we like finite numbers. Next up, we have an implication, right? So if we have a set omega and a function that is continuous from omega to the real numbers, then we know that given that you have a subset of omega and that subset is compact, then the continuous function of a compact set is also going to be compact. Yeah, so compactness is preserved over continuous functions. Very nice argument there. Okay. I think this is the last bit. So, path connectedness. Let's hurry this up. So, path connectedness determines that, okay, given some point and another point, within some manner of set, there is some parameterized function that trails from one point to another through our time parameterization. Typically we use 0 to 1 just because in straight lines it's very easy to deal with. Okay? It can be a little tricky determining what any exact parameterization is, but it becomes very easy to disprove it though. Okay? Another little bit, if you have a continuous function, path connectedness is preserved. So if I take this set with these points and I chuck it through the blender of a function, which just makes a circle, well, if the circle is all that there is, and these 2 points exist inside this, set, and are path connected, and it's a path connected set, then that means they must be together. Too easy, okay? And mind you, this is for every 2 points that exist within this set, okay? Fantastic. All right, example time. So, part A. Use the definition to prove that the unit square is bounded, okay? Unit square is going to be on our R2. We're going to map R here, theta here. Funky variables, I don't know what they're hinting at. So, unit square is given by this. Closed boundaries, I'll just use like red pen to solidify that they are closed, and done. Okay, that's what we have. Is it bounded? Well, what does bounded mean? Bounded means it exists within some distance, and quite clearly we can draw a little ball around here of length √2, and it contains the entire thing. Therefore, it is bounded. For any m distance greater than √2, fantastic. Okay, it is bounded. Fantastic. Use the definition to prove that the unit square is path connected. Ooh, okay. So, given that this is bounded, how do we prove that it is path connected? Well, we define some 2 points, okay? We have a first point, x1, y1 exists here, and another point, y1, y2, that exists here. To prove that it is, path connected, sorry, I'll use green, a different color so you can more easily see. Path connectedness in a square seems awfully trivial because we're only talking about a straight line. And we can quite normally say that, okay, every element within this straight line satisfies the exact same conditions provided. Fantastic. And so, we just do it. Another thing that we could do is we go ahead and we say, okay, take this point, bring it to 0, then put it back to where it was, okay? Because we can define these paths as the conjugation of multiple different parameterized lines, okay? So as long as some manner of sequence of lines exist that are connected, then we can prove path connectedness, okay? This is a very fun property. All right, what was question C? Find the image of f of s where we transpose this manner of mapping to something that looks awfully like, because it is, polar coordinates, right? Within some manner of scale, okay? Note that theta is from 0 to 1, so our angle here is going from 0 to pi on 2. And so that'll actually just almost identical thing, however, we're dealing with a radius now. Radius exists within an argument, and it is from 0, so it includes 0, up to 1 for these manners of arguments. And it is still closed, okay? Now, next up, do we prove that it is still path connected? Well, I mean, is this functional transformation continuous? I think it is, because it's, the composition of elementary functions. And so, through that manner of determination, we can go ahead and say, oh, that sounds awfully like a theorem I just used before. And so, we prove, rather rigorously, with what we have, that, yes, path connectedness is preserved, and so f of s is path connected. All right, so that brings my part to an end. And so, I'll be passing this along to Han. Okay.
So, hello, I'm Han, and I'll be covered for the differentiable functions and integration part. So, without further ado, let's get started. So, we have the limits and continuity for start, and just let's do a bit of recall for what we have learned in first year course. So, in first year, we have limit when x approaches to a fx equals to L. That means that for any epsilon greater than 0, there exists a delta greater than 0 such that if x, absolute value of x take away a is smaller than delta, then we have absolute value of fx take away L, which is our limit, smaller than epsilon. So this is what we learned in first year course. It's for single variable. In this term, we're going to extend from single variable to multivariable. So in this case, we have xy approaches to a and b, and fxy approaches to L. So this is basically the same. It's just an extension from what we have learned in first year. You can see we just basically change x to xy, and we change a to ab. And also, you can extend to the 3-dimension and 4-dimension or even 5th dimension, because what ultimately we have is a point in a space, and we are approaching that point to A, B, C, and D if it's in high dimension, approaching to this point. And if that distance is smaller than delta, then we have the limit. Okay. So a function f of two variable is called continuous at a and b if limit of xy approaches in ab fxy is equal to fab. So we said it's continuous on D if continuous at every point of AB. So there's a very important fact. So the main difference to the case of one-dimensional domain is that in two-dimensional or even higher dimension, we can approach from a point from infinitely many directions comparing to only left and right in the two dimensions. So in our two-dimension case, if we're saying that we get the limit. If the limit exists, we want to check if the limit exists. We have to say, okay, from the left directions, it's approaching from 2, 1. And from the right directions, it's approaching to 1 as well. But in our two-dimension case, in our three-dimension case, or even higher, we can approach in a point from limited directions. Limited curves. Okay. Approaching that point from a lot of curves, or even some crazy curves. Okay, to that point. So here's our past exam questions. So let f be defined as the following. X as the following over here, and by considering appropriate curves that approach to the origin, or otherwise we prove fxy is not continuous in 0, 0. Cool. So if xy is continuous at 0, 0, then limit xy approaches to 0, 0, fxy has to be 1. But if we can find a curve that is approaching to 0, 0 that is not equal to 1, then the limit does not exist. That means our function is not continuous. Okay, so we have, for example, we can have y equal to mx, approaching from y equal to mx, and we substitute y equal to mx into the functions. What we get is f equals x squared plus x times mx, that will be mx squared. And then we have m plus m squared x squared. Cool. And for our denominator, what we have is x squared plus m squared x squared. And we can cancel x squared, which give us 1 plus m squared over 1 plus m squared. Okay, so if m is equal to 0, then we do get 1. But if m is equal to 1, then we get 3 over 2. If m is equal to 2, we get another value, which is also not equal to 1. Thus, we can prove that the limit does not exist and our functions is not continuous. Okay, cool. Let's go to the partial derivatives. So the partial derivative fx with respect to x of a function f of two variables is a function of two variables obtained by holding y constants and differentiating with respect to x. So if we're getting a partial derivative with respect to x, this case, we basically consider y is just a constant and we're differentiating with respect to x. And it's very similar for to get the partial derivative with respect to y. It's over here. Okay, chain rule. So if we are encountering the questions that involve chain rule, then the first thing we need to do is to draw a diagram. So a function f is differentiable functions of two variables x and y. So we have functions f over here, and it's depending on two variables x and y. And then x and y are differentiable functions of two variables s and t, which they are depending on s and t. So if we're going to get the partial derivative of f with respect to s, okay, so we can go into this way. So we take the partial derivative with respect to, with respect to x first, and then take partial derivative with respect to s in this directions. Or we can have take the partial derivative with respect to y first, and then s. So this is essentially our green path, and here is our yellow path. Wonderful. And also, if we are going to take partial derivative with respect to t, then we can go into these two directions. Okay, we take with respect to x first, and then with respect to t. Or we can have, we take respect to y first, and then we go into t. So this is our pink path, and here's our blue path. So that's our chain rule. So whenever you see the questions that involve chain rule, I highly recommend to draw a diagram so you know, okay, which paths I'm going and which paths I'm missing. So make sure you won't make a mistake at the end. Okay. So here's the past exam questions. So use the chain rule to find, with respect to r, the partial derivative with respect to r, and with respect to s, and then with respect to s and r. Okay, cool. So our first step, as usual, we draw the diagram. So we have z, or in other words, f, is depending on u and v. Wonderful. And we have r and s. u and v is depending on r and s. Ooh, good. So if we're going to calculate the partial derivative with respect to r, then what we get is, okay, we have the partial derivative with respect to u first, and then we take partial derivative u with respect to r. So this is our, here's our path, this way. Okay, so what other paths do we need? We also have take the partial derivative of f with respect to v first, and then we take partial derivative of v with respect to r. So this is our yellow path. Okay. Then we want to get, so solve this one. And then we need to solve the partial derivative of z with respect to s. So we have, similarly, I would not explain this one, but it's very similar to the previous case. It's a partial derivative of f with respect to u first, and then we take partial derivative of u with respect to s, plus partial derivative of f with respect to v first, and take partial derivative of v with respect to s. Wonderful. So those two are not very hard, and if you further, like plugging u equal to 2r, take away s, and v equal to r plus s squared, and for example you differentiate this part, nice thing. So that's u. Okay, if you simplify that, you can get the following. Similar, you can get the following. And what is a bit hard is the second partial derivative over here. Okay, so I'll still just quickly draw the diagram so we can use a diagram. Okay, that's U, V, R, S. Okay, so what we have is, we have take the partial derivative of s with respect to s, and also take the partial derivative with respect to r. So we plug in the value over here, and this is what we get. Okay, this is just what we get over here. Or in other words, you can use the value over here, the result. Okay, we'll substitute inside. And then we basically take in this part with respect to s. So what we essentially do, we can replace the f over here with partial derivative of f with respect to u. So in this scenario, we can get the following. Because we're replacing f with partial derivative of f with respect to u. So you can think of this one is equal to f u. And then you're taking with respect to u, which is f u u in times partial derivative of u with respect to with respect to s. Okay, with respect to s. Or you can have f u v, this directions. And taking the partial derivative of u v with respect to s. And don't forget the 2 over here, because the constants you could just like substitute inside, and finally you can get the following. And it's very similar for this term over here, because you just, instead of replacing with the partial derivative of fu, you can replace with fv. Okay, cool. And to use the similar formula, you can get the following. And after further simplify, you will get the final result. Hopefully it's not going to be too hard. All right, then we go to the Jacobian matrix. So if all partial derivative of f exist at a point that is belong to omega, then the Jacobian matrix of f at a will be presented as following. So what we have, you see, we have f1, f1, and f1. So we derive f1 with respect to x1, with respect to x1, x2, and xn. And for the second row, we have f2, and all the way f2. And we derive f2 with respect to x1, x2, and all the way to xn. Okay, it's very similar. And for the last row, we have the similar pattern. fm, fm, fn. And we have x1 all the way to xn. Cool. All right, we go to the fn maps. So the functions t is called fn if there exists a y0 and a linear map L such that the t is equal to y0 plus L. So what we essentially have is, so for here, we have the point vector. So our y0 is our point vector. And our L is our linear map. Okay, so our functions f has an alpha approximation at a point A if there exists a matrix A and a vector B such that, okay, we have the limit over here. So what we have essentially here is actually f, okay, fx. Approximately, we can use the alpha approximation to approximate to ax plus b. Wait. Okay. Okay, and here is just our weighting. Okay. Cool. Then why do we need the alpha approximation? Is that we need alpha approximation to define differentiability. So our function f is said to be differentiable at A if f has an alpha approximation at A. So what we have is the following. So it's basically extension for what we have shown in the previous slides. So fx here can be approximate to FA plus the Jacobian matrix of A times X take away A. So here is our position vector. Our Jacobian matrix will be our direction. Okay, cool. And there's one thing I noticed is very interesting is because when X is approaches to A, over here, then the absolute value of X take away H will also approach to 0, right? But the function also need to be 0. That means our denominator has to approach to 0 quicker than our numerator has to approach to 0 quicker than our denominator. So it has to approach to 0 quicker. So that's why. And then we can finally get our limit is equal to 0. Otherwise, it's not possible. Okay, we have a past exam questions related to alpha and approximations, and we'll quickly go through it. So, recall our alpha and approximation formula. It would be the following. G of x equals to FA plus Jacobian matrix times the difference between x and a. And first step, we compute the Jacobian matrix. Hopefully everyone can compute the Jacobian matrix. We get the 2x, 2y, and two functions related involving cosh. Okay, that's our first step. Step 1, find the Jacobian matrix. And our step 2 is basically apply the formula. So we have the formula over here, we just substitute value inside. Okay, cool. We have 2, 0. That's when we substitute the point x equal to 1 and y equal to 1 into the functions over here, and we can get 2, 0. And we also substitute x equal to 1 and y equal to 1 into our Jacobian matrix, and we can get the 2, 2, 2, and negative 2. And finally, we have this part, which is x minus a. Cool. And x here, we can write matrix xy. And after we expand our matrix and do a bit of simplifications and calculations, we can get the following. So you can write in this way: 2x plus 2y take away 2, 2x take away 2y, like that. Cool. Gradient. So for our omega and our f, the Jacobian matrix referred as a gradient. We use this way to define the gradients. So that's our first row, you can see. Or we use another way, which is for MATH2011. We suppose f is a function of two variables, and fx and fy are continuous at a and b, then the gradient of f. It's just simply that. This is partial derivative of f with respect to x and partial derivative of f with respect to y. And we evaluate those derivatives at the point a, b. Cool. There are two important theorems related to gradient. So the first one, the maximum and minimum value of our derivative are at plus or minus the size of our gradient, and occur in the directions given by here. Okay, this is very easy to prove because what we have is f u. Okay, that's our derivative. We can say that's equal to our nabla of f times cosine phi. Okay, so this is the relative angle to our nabla f. So when we're saying the maximum or minimum, that's nabla phi. It's just from -1 to 1. So it's either plus or minus. So that's our maximum and minimum value. Okay, cool. And then we have another theorem, which is our nabla f is normal to the level curve passing through x0, provided that fy are continuous. What does it mean by this? It's, for example, we have a contour over here, and our normal, so our nebula f, is normal to the level curve, which means it could be this way. It's normal, right angle, to our contour. So that's the directions of our nebula f. Okay, the directional derivative. So let omega and f be functions. Let a be an interior point of omega and u be a unit vector in Rn. So the direction derivative f in the direction u at a is defined as the following. Okay, so you don't have to look all of these on the slides, but what is important is over here. So basically saying that we have the nebula f, the gradient, and times the unit vector, u. Okay, this one's important. We have past exam questions about the luminosity. Define the luminosity L as the following. So, the questions ask, find the rate of the change of the luminosity at point 1, -1, 1 in the directions of the vector. Okay, so our first step is to find our gradient. So what is our gradient? Nebula L. I will just simply take the partial derivative with respect to x and y and z. Okay, and what we can get is the following. If we do a bit of simplifications, we can get negative 1/8i plus 1/8j, take away 1/4 k. Okay, so we have our nebula L. And how do we find the directional derivative? We need our unit vector, okay? So just recall, we have the nebula L, we need our unit vector. Okay, so how do you find a unit vector? So in the directions of a vector 1, 1, 1, and our unit vector will be just simply 1, 1, 1. But don't forget, we have to divide the vector by its magnitude, so it will be 1/√3. So that's our unit vector. And finally, our rate of change, which is also another way, directional derivative, will just be nebula L times v, our unit vector. Okay, nebula L times our unit vector, and it's approximately equal to -1/4√3. Okay. And the second part of the questions is, in which direction does L change most rapidly at point 1, -1, 1? And what is the maximum rate of change of L at 1, -1, 1? So, based on the two important theorems we have just explored, the maximum rate of change of L at point 1, -1, 1 occur in the directions given by nebula L. So which is the following? We have just calculated it. And the maximum rate of change of L, which is the size of it, and it's approximately equal to 0.306. Okay. Tangents and norm. So for a surface S defined by phi equal to a constant, the tangent plane at P belongs to S is a plane through P with normal, okay, nebula phi at the point P. Okay, from this definition, we can immediately write it down, the point normal form. Okay, the tangent plane at P. So this is our gradient, and also we are going through the point P. So x take away P times the normal, and that is our tangent plane. And on our normals, for a surface in R3, the normal line in P is just some line that is normal to the tangent plane. Cool. We have a practice questions. So find the tangent plane and normal line to the ellipsoid 2x squared plus 2y squared plus z squared equal to 8 at the point 1, 1, and 2. So the first step, we find the nebula f. So here is our functions we define as f. Nebula f, that would be 4x, 4y, and 2z. Okay. If we substitute the value 1, 1, 2 inside, what we get is 4, 4, 4. Oh, nice. Okay, and our tangent plane would just be our gradient, our nebula f times x minus, we can x, y, z, okay, x minus our point. This is the point we go through, equal to 0. And if we expand this, we can get the following functions. So we can get 4x plus 4y plus 4z equals to 16. Or you can further simplify, that would be x plus y plus z equal to 4. Okay, that's our tangent plane. And also we have the normal line. Okay, our normal. So that would be, it's a line. We go through point 1, 1, 2 plus t times our directions, which is our 4, 4, 4, or we can further simplify 1, 1, 1. So yeah, this is our normal line. Cool, so we have our tangent plane and normal line. All right, then we'll go through two-variable Taylor series. So the two-variable Taylor series expansion of xy around the point x0 and y0 is given by the following. Okay, so this is our Taylor expansion, and I do want you guys to know the coefficients. All right, so the coefficients here is 1. We have the 2 here and 1. We have 1, 3, 3, and 1. So you notice this is a pattern of Pascal triangle. So just keep that in mind. The coefficients inside is actually a Pascal triangle. And for the rest, it's just the first partial derivative, and we have second partial derivative or even third partial derivative. All right, so this is a very important formula. If you can bring a cheat sheet to the exam, I highly recommend to write down the equations and formula. Okay. All right, so we have a Taylor series problem. Taylor series problem. All right, so we have f equals to the exponential functions x squared take away y, and we want to find the Taylor series of f about 1, 1 to the second order. Okay, cool. So our first step is find the partial derivative with respect to x. So what we have is 2x and times the exponential x squared take away y, okay? And then we have take the partial derivative with respect to y. We have the negative exponential x squared plus take away y. Okay, and then also second derivative with respect to x. You can have 4x squared plus 2 exp, okay, exponential x squared take away y. Wonderful. Also, okay, second derivative with respect to y, we have the exponential x squared take away y. Also, in this case, I'm just gonna quickly write it down. You can do the calculations again once you get time. Okay, cool. So we're at the point 1, 1. Evaluate the point around 1, 1. So if we plug in inside, that would be 2. So this one, 2. Okay, here, negative 1. Okay, here, 6. Here, 1. And here, negative 2. Okay, After we get all the derivatives we want, then we just need to plug in the value. So our formula, recall, you can see the slides from previous slides. Check the formula. Our tail expansion. Okay. First, we have plug in the value f11. Okay. And then plus 1 over 1 factorial times 2 x take away 1 minus y take away 1. Okay. And then we have 1 over 2 factorial, 6 times x take away 1 squared. And then we have, don't forget our 2 over here, our coefficients is 2. So in total, I have 4 times x take away 1 and y take away 1. And then plus y take away 1 squared. Okay, and plus dot dot dot. So this is our tail expansion, and if you substitute f11, that would just be 1. Okay, cool. So this is our tail expansion. It's only asked up to second order, so you can just leave it here. Okay. We have the critical points. Definition. So let f be a function. A critical point of f is a point AB where nabla f is either 0 or does not exist. Our nabla f, our gradient, is either 0 or does not exist. Okay, so our stationary point of f is a point AB where nabla f is 0. All right, we have the local maximum and minimum, which is the largest and smallest functions value. Maxima, minima, and the saddle points. So stationary point is our nabla f is equal to 0, and our global maximum, global minimum, all of these. Quickly run through it. And our local maximum, local minimum, and our saddle point. Saddle point here is very special. Okay, so it's neither a maximum nor a minimum. Second derivative. So, suppose the second order partial derivative f are continuous on a disk with center AB, and suppose that the partial derivative with respect to x equal to partial derivative with respect to y, and they are at point AB, and they are all equal to 0. And this means A and B is a critical point. So our second derivative, the main part is just over here, okay? I just use this formula. So if our derivative is greater than 0, it's a saddle point immediately. If the determinant is less than 0 and our second derivative with respect to x is greater than 0, it's a local minimum. If our determinant is smaller than 0 and our second derivative with respect to s is smaller than 0 as well, it's a local maximum. Okay, past questions. So f(xy) defined as here, show that 1 and -1 is a saddle point. So all we need to do is just show our determinant is greater than 0. Then it's a saddle point immediately. Okay, so how do we show the determinant is greater than 0? Well, we have take the derivative, the first derivative and the second derivative all the way listed here, and we apply the formula, which is our xy, and take away fx times fyy. Okay, it's over here. And we just substitute the value inside. We can get 288. And that's bigger than 0, which means it's a saddle point. Okay. And then show that f has another critical point and find out what type is it. So back to our nabla f, our gradient. So we have another solutions. We want to find another solutions. Okay. And if we set our nabla f equal to 0, we can get another solutions, which is 5 and -5. And we want to determine its type. So we need to get our determinant to check if it's greater than 0 or less than 0. Okay, and it turns out that applying the same formula, we get the fxy, and we take the same formula, get fx and fyy, and plug in the value f in the -5, we get the following. It's negative 288, which is less than 0. Okay, and then we need to check our fxx is 36 greater than 0. That means it's a local minimum. So we just use the second derivative test. We can determine its type. Fantastic. So we have next one. We have the Lagrange multipliers. Okay, so suppose f and phi are differentiable and as defined at the following. It's a smooth surface in Rn. So if f contains a local maximum or minimum at point A, then our nabla f and nabla phi are parallel. What is important is the formula over here. Okay, so it's nabla f equals to lambda times nabla phi. This one's very important. Past exam questions. So a rectangular box has 3 of its face on a coordinate plane and on one vertex in the first octant. And on a paraboloid, Z, determine the maximum value of the box. Okay, so our first step is actually define f and g. So remember our Lagrange multiplier, we need to have 2 functions. So we need to get to know what are the 2 functions. So f, x, y, and z, because it's a rectangular box, so our formula would just be over here. Okay. And our constraint is our paraboloid. Z, take away x squared, take away y squared. Okay, after we have defined f and g, we need to apply the Lagrange multipliers formula. We can get the nabla f and nabla g. We're just writing those 2. And then all we need to do is just use the formula. Nabla of f equals to lambda times nabla of g. Okay. So okay, so what we have is we have y of z equals to lambda times -2x, x of z equals to lambda times -2y, x and y equals to lambda times -1. Don't forget our constraint. Z equals to 4, take away x squared and y squared. And if we represent the lambda in terms of yz, 2x. Okay, that's just a bit of calculations over here. X, y, -1. Finally, we can represent our x squared in terms of z, which is x squared equal to z over 2, and y squared equal to z over 2. And you're plugging those 2 values into our constraint over here. And finally, what we get is z equals to 2. And our x accordingly is 1 and y is equal to 1. So our maximum value would just be 1 times 1 times 2, which is 2. Okay. So here we are, our maximum value 2. Cool. Inverse function theorem. So if omega be open and A belongs to omega, f will be continuously differentiable. Okay, so here is if it's an invertible matrix, then f is invertible on an open set containing A. Okay, so what is important here for the inverse matrix is to check the Jacobian of f is an invertible matrix. That means our determinant determinant cannot be 0. If the determinant is not a 0, then it has inverse functions. We can apply the inverse functions theorem, which means it has an inverse functions. Okay. And our Jacobian matrix would just be like that. Okay, so past exam questions. So let f be R2 to R2 and given by fxy equal to that one. So find the Jacobian matrix. Easy to find, that's our F1 and F2, okay. And we just take the partial derivative of F1 with respect to x and partial derivative of F1 with respect to y. And here's partial derivative of F2 with respect to x and with respect to y. You get the following, this one. And okay, so second part is at the origin. So we plug in the value 0, 0 inside, we get the following here. Because it's very easy to get a determinant of the Jacobian matrix, basically 3 take over 0, that just be 3. So it's a non-zero, and by the inverse function theorem, f is a differentiable inverse around 0, 0. Cool. And then we'll go to the integration part. Okay, first part, Fubini theorem. So let f from R to R be continuous on a rectangular domain R, AB times CD. So rectangular domain. And we have two integral here. So what I mean by this is actually, it just like say that if f is continuous on a rectangular domain, then we can change the sequence of the bond. Like the first one is from C to D, and evaluate from A to B. We can evaluate from A to B first, and then C to D. So this means that as long as the above conditions are satisfied, we're allowed to rearrange and manipulate our integral however we want. Okay, so here's our practice questions. Calculate the double integral of y times sine xy dA over the rectangular domain 1, 2, and then maps to 0 and pi. So what we have here is, okay, we have the integral you can use from 0 to pi, and then 1, 2, okay, we can have the dx dy, y sine xy. And that is equal to double integral of 1 to 0 to pi dy dx y sine xy. So that means basically they're the same. We're just changing the sequence of the bond, right? Okay, cool. And we can just select one of them to evaluate it because they're exactly the same. And however the calculations is simpler, we can just use that way. And in this scenario, I would say I will use the first one. This one's simpler. So after we plug in the value, okay, we evaluate the inside integral first. That just be 1 times negative 1 over y times cosine xy, and that's from 1 to 2 in dy. Okay, and after you do the calculation, that would be sine 1 take away a half sine 2y. Evaluate from 0 to pi, that's 0. Okay. Why can we use the Fubini theorem? It's because it's continuous. The functions of it here is continuous. And it's easy to see because y is continuous and sine xy is continuous. When two continuous functions times together, it's also continuous. Okay, cool. Double integral. So we use double integration to find an area of a region bounded by those three curves. Let's also practice questions. Okay, this graph, so when we encounter the questions that involve integrations, the first thing we need to do is draw the diagram. Okay, so we have the bound y equal to the square root of x, which is in this way. Okay, and we have y equal to x and y equal to x over 2. And the region we are bounded by those three curves is over here. Okay, and if you want to represent this just within one integral, it's probably not possible, because what you can see is, for example, if we evaluate dy, you have a little square, evaluate to dy, then it's bound by y equal to x first. And if you evaluate dy, but this scenario, it's bound by square root of x. It's bounded by two different functions. So that means we somehow need to break into two parts and find the integral with respect to those two areas, 1 and 2, and add them up at the end. So we find the integral for the first part. You have ff dy dx. Because it's just the area, okay, so we just put in 1 over inside of for the integral. And now we need to determine the bound. So for y, we're evaluating from this line to that line, right? So what we have is from x over 2 to x. And for x, we need to find the intersections over here. So the intersection here is 1, 1. It's easy to get. The intersection over here is 4, 2. So for x, our bound is from 0 to 1. Okay, this part. So that's our first part integral. And also, we need our second part integral, which is dy dx as well. 1 for the integral. Now we need to determine our bound. So it's from this line, okay, to that line. So that's our bound. So also starting from x over 2, okay? But this time, our upper bound is no longer x. Upper bound is square root of x. And for our x bound, that's from 1 all the way to 4, so 1 to 4. So that's our integral. For the rest part, it's just the calculations, and the final answer is 7 over 6. Okay, cool. Double integral. There's a special case, so this is for the Cartesian form. We also have the polar coordinates form. So for our polar coordinates, our x is equal to r cosine theta, our y is equal to r sine theta, and we have the x squared plus y squared equal to r squared. Okay, and our integral is a bit special. We have to times r for our integrand. We're representing r theta for f, and times the integrand r dr d theta. Why we need to times the r here? That's because that's our Jacobian matrix, and we will elaborate this in the change variable part. But now all we need to do, just keep that in mind. We need the r over here for our integrand inside of the integral. Okay, cool. So use our polar coordinate to find the integral over here. And where our omega, our contour, is x squared plus y squared smaller than or equal to 1, and xy has to be greater than or equal to 0. First step, draw the diagram. Okay, it's very easy to draw in this case because our contour here is just a circle, right? With a radius 1. And since x and y has to be greater than 0, it's the part over here. Alright, so okay, we have the integral dr d theta. Don't forget we have an r over here. And we represent x in terms of r times cosine theta, y in terms of r times sine theta. So that would be r squared cosine theta squared times r cubed sine theta cubed times r. So now we need to determine the bound. For r first in theta. So for our r is 0 to 1, right? This one is basically our r squared. So r is just 0 to 1. And for our theta, we have, because it's in the first quadrant, so 0 to pi over 2. Wonderful. So 0 to pi over 2, and simplify this. Okay. We can get r to the power of 7 over 7, 0, 1, d theta. We'll not go through the calculations anymore, but final answer is 2 over 105. Cool. That's for the polar coordinates. We'll then go to the triple integral. So find a formula for the volume tetrahedral bounded by the plane given by the equations over here, x, y, z, all has to be greater than or equal to 0, where a, b, c are greater than 0. So this is our Cartesian form. Cartesian form. Okay. First step, as usual, we draw the diagram. So this is our z-axis, our x-axis, and y-axis. Our bound, x-coordinate A, y-coordinate B, z will be C. Okay, so when x, y, and z equal to 0, we get the x-coordinates, that's A, and similarly we could get the other coordinates. So this is our tetrahedral. Okay, looks nice. Okay, so here we need to use the triple integral over here. Because it's a volume, it's not the mass or something. If it's mass, you have to put the density functions for the integrand, but it's volume, just means the density is a constant, and here just use 1. Okay, we have the dz, dy, and dx. So for our dz, dy, and dx, let me write x again. Okay. You could think about little cubed. Just think about little cubed inside. And for our dz, we need to find the bound for z. That means in the z directions. Okay, have a little cubed accumulate, and we're finally bound by this plane, right? Okay. Oh, finally we're bound by this plane. So that's from 0 to the plane over here, which can use this formula to get. So how do we get the plane for z? So basically, we can use z over c, that's equal to 1, take away x over a, and take away y over b. We'll just move those two parts to the other side. And z would just be the right-hand side, the whole part in the right-hand side, times c, right? Times c. Okay, so this is our bound. We have successfully represented the plane over here. So this is our bound. Okay, so we just write it down. 1, take away x over a, y over b, times c. Wonderful. And now we need to consider the bound for y. Starting from 0, but where is the bound? So we're looking at the xy plane in this case. Okay, xy plane. So you have the y over here and x over here. Cool. So xy plane would just be this line. Okay, so straight line. Okay, and it's very easy to represent. This is just y equals to b over a x plus b, because the y coordinates here is b and x intercepts a. Okay, cool. That's just over here. So our bound could be represented as a x plus b. So that's our upper bound for y. And finally, our bound for x is very easy, from 0 to a. Okay, cool. So we get the integral. And finally, after we evaluate it, we will get ABC over 6, which is exactly the formula we have for tetrahedra. So nice. Okay. We have the triple integral for cylindrical coordinates. Okay. No worries, because the picture is not loading here. Okay. Just wait for a bit. Okay, cool. Pictures is not working here, but we can draw the picture. So, alright. We have the cylindrical coordinates. So what you can think about is, in our 3D, okay, like that. We have a Z. So this is our Z plane, Z. And here is our R. Okay. Here is our R. Here's our Z. And we got an angle over here. So where is our angle? We have angle here, theta. So this is a 3D plane. We have the X, Y, and Z. And here is a line. This is our Z. We have theta. There's 3 important parts, theta, R, and Z. Okay, this is our cylindrical coordinate. Cool. And here's an important information. So Z is still equal to 0 as a Cartesian coordinates. But r squared equals to x squared plus y squared. Hopefully, we're all familiar with this. X equal to r cosine theta, and y equal to r sine theta. Okay, those are the 4 things we need to know for cylindrical coordinates. And also, don't forget the integral we have. So, previously, we have the x, y, z, and the dz, dy, dx. Now, we're using the triple integral for cylindrical coordinates. Then we represent in terms of r, theta, and z. So r, theta, and z. And then we need to time r over here, don't forget. Okay, it's very similar to the polar coordinates. We need to time r, and it's big. Why is that? That's the determinant for our Jacobian matrix, and that's for the change variable part. We'll save it. Okay, d theta. Okay, cool. So 4 important formula and 1 integral. Okay, 4 plus 1, 5 important concepts we need to know for cylindrical coordinates. And here is a practice questions. So evaluate the integral over here, where S is a solid bounded by the paraboloid and the plane Z equal to 0 and the cylinder. So once you solve the questions that involve like cylinder, then probably you have to use the cylindrical coordinates. That's actually a hint for you, okay? That would be easier for you to use the cylindrical coordinates to evaluate the integral. Okay, cool. So first step, as usual, we draw the diagram. We draw the paraboloid, and we have the cylinder, and Z equal to 0. We draw the diagram. Okay, this is a 3D. We draw the paraboloid first. Okay, cool. And where is our cylinder? It's over here. We have a cylinder here. These are the intersections. Don't forget we have the Z equal to 0 plane, which is just this plane, okay? And the solar volume bounded by the 3 plane would just be this part, or use your imagination, okay? All right, so after we have drawn the graph, write down the integral. We use dz, dr, d theta. Don't forget we have r inside of the integral. Okay, cool. And now what we need to do is just represent x squared plus y squared in terms of the cylindrical coordinates. That just be r squared, very easy. And now the hard part is we need to determine the bound for z, r, and theta. So for z first. Okay, so for z it's actually not hard because from the 0, our lower bound is very easy. We'll get 0 already. And for our upper bound, we just need to plug in a value over here, which is z equal to r squared over 2. That's our upper bound, right? So you can imagine you have a little cube over here, and it's adding up, accumulating all the way to here, or it's bound by this one. What is that one? It's our paraboloid. So we're just plugging value here. So that just be r squared over 2. Okay, solved. How about our r? R is not bad because it's starting from the origin. Okay, all the way to here, origin is 0. All the way to here, we have the cylinder x squared plus y squared equal to 16. That means here is 4, right? Our radius 0 to 4. And finally, we need to rotate, right? If we ignore this part, then we just evaluate a piece of sheet. Remember, imagine piece of sheet or like here, and then it has to, if it's volume, it has to rotate. So that means we evaluate from 0 to 2 pi, and that's d theta. Okay, so here's our integral. And I'm not going to evaluate here. And finally, what you get is 2 to the power of 11 over 3 and pi. Okay, that's our final answer. Similarly, we have for spherical coordinates. The picture is not working, but we can draw, no worries. Okay, so for our spherical coordinates, it's actually a bit hard to draw, but yeah, why not? Let's give it a try. Okay, we have, here's another column. We have that. So this is our integral. Here is our row. So this red line is our row. That's the length from the origin all the way to here. You could think about robot. So the robot is standing at the origin, and its arm is all the way extending to this point, and the distance is rho. Okay, and also I have a phi here. This is our phi. Imagine if this line has a projections on the xy plane, and then the angle between this projection line to x axis is our theta. So ultimately we have three variables. So we have the phi, we have the rho, and theta. Okay. There's a few formulas that we need to know. First one, x squared plus y squared plus z squared equal to rho squared. Z equals to rho times cosine phi. Okay. So cosine phi. Think about this one. Our z is our cosine rho, right? Cosine phi times rho, right? Okay. And x equal to rho sine phi times cosine theta. Y equals to rho times sine phi sine theta. Okay. There's one trick so you can remember about that formula is that for y it's always sine phi and sine theta. Okay. And for x it's sine and cosine. This for the integral, we used to have the Cartesian form fx, y, z, and dx, dy, dz, and then that's equal to the triple integral. We'll represent f in terms of rho, phi, and theta. And we times, inside of the integral, very important, we times rho squared sine phi d rho, d phi, d theta. Okay, so there is a four formulas as a previous example as well. The cylindrical coordinates. For spherical coordinates, we have four important formula and one integral as well. So 4 plus 1. Okay. Spherical coordinates. Wonderful. We express the volume V of the region above the coin and inside the sphere using the spherical coordinates and evaluate its volume. As usual, we draw the diagram. Okay, so we have the coin over here. It's easy to draw because it just over like that. Okay. And for our sphere, we need to know where is our center. So we could change a bit. How do we change? X squared plus y squared and plus z squared. Take away 2az. We're completing the squared plus a squared plus a squared. And finally, what we get is x squared plus y squared plus z minus a squared and a squared. That means our center is 0, 0, a. Okay, 0, 0, 8. This point is our a. And our radius is a as well. So it's approximately look like that. It's like a sphere. Okay. Okay, probably this one has to look bigger. Okay, like this one. The coin is like that. And our sphere. Okay, cool. Looks like that. Let's go through the origin. And the volume that is above the coin and inside the sphere will be this part. It looks like ice cream. Okay, so it's with a coin and have the like a ball at the top. Nice. So then we need to have our triple integral. After we have drawn the diagram. d rho, d phi, d theta. And don't forget, inside of our integral, we need to have rho squared times sine phi. Okay, cool. So because it's a volume and it's not calculating the mass, so we'll just say 1 over here. If it's calculating mass, we need the density functions over here. And also, our bound will be 0 to, okay, we have to determine the bound for rho, phi, and theta. How do we define that? We'll look in our graph. Okay, rho is always starting from the origin and all the way to here. So this is our rho. Okay, so how can we find the bound for rho? Linking it here. This part. The intersections here is 2a. Why is that? Because our center is z equals to a and 0, 0, a, right? And so it's over here. And our radius is a. So our z-intercept will be just 2, 8. And rho is this green line over here. This is a black line. So this is rho is over here. So that means rho, our upper bound, is equal to 2a times cosine phi. This is our phi angle, okay? Because this is a right angle, so our rho will just be 2a times cosine phi. 2a times cosine phi. And we need to determine the angle for phi. P will be over here all the way to this bottom, right? It takes a bit of time. Why it's moving? Okay. Hopefully it's not moving again. Okay. We have the cone over here. And this angle, because the A is over here and our radius you can see is also A, so that means this angle is pi over 4. Alright, so our bound for phi is 0 to pi over 4. And then we need to determine the bound for theta. Where is our theta? Theta is, you see the graph? It's all the way around here. So just 0 to 2 pi, it's very obvious. So 0 to 2 pi. So get the integral over here. Get the integral over here. All we need to do is just evaluate. And we'll not evaluate this time, and you can find a time to evaluate, all right? Okay, cool. So that's for the spherical coordinates. Change of variable. So why do we need like times rho squared and sine phi for like spherical coordinates, or like times rho or times r for cylindrical coordinates and polar coordinates? Why do we need to time all of these inside the integral? It's because of the change variable. We're essentially talking about it. Okay, so let omega and f be an injective and continuously differentiable functions such as the determinant is not 0 for all x belongs to omega. If f is any function that is integrable on omega dash f omega, then we have the following formula. So you see, we have the formula substitutions. We just use that one, x equal to r cosine theta, y equal to r sine theta, where our I is greater than 0, and our Jacobian determinants is r. So that means we need to times r inside of our integral. Okay. So here's an example. So evaluate the double integral x plus 2y squared and xy dx dy, where omega is the region in the first quadrant bounded by the curve, both four curves. All right, So unfortunately the pictures is not showing, but no worries, we can draw. We like drawing. Okay, so we have y squared equals to x, so that's our y squared equal to x. And we also have y squared equal to x take away 1, y squared equal to x take away 1. And also we have xy equal to 1, in other words, y equal to 1 over x. Okay, y equal to 1 over x. And we also have y equal to 2 over x. Okay, the graph is very simple, and the bounded region just be the middle part. Okay, cool. And then change the variable. We define u equals to x take away y squared, and v equals to xy. And want to determine its bound. Very easy to find a bound. Why is that? Because if u equals to y squared plus take away x, that would be just from 0 to 1, right? You could 0, oh sorry, it's other way around. So x take away y squared. So that just be 0 to 1 for u. Yeah, 0 to 1. And v, xy, that would be 1 to 2. Okay, cool. So we have u here, v here, u, the bound for u and bound for v. Wonderful. Second step, take the Jacobian. So first step, draw the graph, and then we determine, define u and v, and found the bound for u and v. Second step, the Jacobian matrix. So we're supposed to actually find dx, take the partial derivative of x with respect to u, and take the partial derivative of x with respect to v, and partial derivative of y respect to u, and partial derivative of y respect to v. But this case is very, it's kind of very cumbersome to represent x in terms of u and v, like around here. So instead, we define in this way. Take the Jacobian matrix of G. Let's take a partial derivative of u with respect to x. Okay, and then finally, for the determinant, we just take the inverse because we have the inverse functions area here. Okay, so what we have is we get the Jacobian matrix for G in this way. Okay, why is that? Because we can have here, okay, so that's x take away y squared and xy. All right, use this formula. That's our u and v. Take this formula, we get the following matrix. And our determinant would just be the inverse of it. So the inverse for the determinant for Jacobian matrix G will be x plus 2y squared. And then the determinant for Jacobian matrix F would just be 1 over x plus 2y squared. Cool. And our integral right now, 0 to 1, 1 to 2, representing v, dv, du. Okay, 0, 1, v squared, 2, du, 3 over 2, du. Finally, we get 3 over 2. So that's our final answer. Because I times the Jacobian matrix over here and into our integral, that means we'll cancel out these terms. And xy just our v. So that's why we simplify a lot. So we get the v for integral, just v here. And it's from the bound 1 to 2 and 0 to 1. Okay, cool. The last part is our Leibniz rule, the differentiation under the integral sign. So essentially, what is important is here. Okay, this part is very important. So put our integral inside for the first part, and then we have the following. We have the plus sign and minus sign here. Okay, so we'll quickly run through the atypical questions that are related to the Leibniz rule. Okay, over here. So this question is essentially a direct application of Leibniz rule. Cool. And we have conditions to check if we can use Leibniz rule or not. So this, we need to do a bit of recap over here. So let A, B be constants, A smaller than B at phi 1, phi 2, and be a continuous function such that phi 1, x and phi is smaller than or equal to phi 2x for all x belongs to A and B. If f and the derivative with respect to x are continuous on the origin, then we have the functions over here. Okay, we have a bunch of conditions to check. So, alright, so first note, our integrand is continuous across the entire boundary for x greater than 1. And furthermore, then x, the y over here, is bounded by x and x squared, which you can see. Okay, our y here is bounded by our phi 1 and phi 2, which is our x and x squared. Okay, x and x squared. Additionally, we have the partial derivative of f with respect to x is over here. Alright, so that satisfies the conditions. Our partials are continuous on origins. So our partials do continuous on origins. So thus the partial derivative of the integrand is continuous everywhere. Okay, it's stating here. Therefore, we can apply the Leibniz rule. So if all the conditions over here are satisfied, then we can use the Leibniz rule. And then we just need to plug in the formula. First step, we put our derivative inside of functions. Okay, just like that. And then we substitute y equal to x squared, our upper bound, and we differentiate with respect to x squared, which is 2x. And then plus and minus sign, we substitute y equal to x, and then we differentiate with respect to x1. Okay, all good. And then we just need to further simplify our functions. And finally, we will get the following. Okay, so this is at the end the part of the differentiable functions and the integrations. If you have any questions, you can ask right now. Otherwise, I will use the example to wrap up here. Okay, thank you.
All right. Good luck, everyone, with the studies and yeah, good luck for your exams and good luck with your studies. We'll see you tomorrow.